tree. So you now know about this binary search tree. What is binary search tree? You know about this one of the balance tree. That is what AVL tree. Okay. Now we'll see another thing, that is MV search tree. Okay. So in MV search tree, it is a kind of data structure where you store the data in a tree, but it is not like a binary search. Uh, it's a kind of what is a fat tree, you can say. So order of the tree is given to you. आपको एक tree का order दिया होता है. That is how many children could be there. So I will just open the thing for you. Let me check for this. T OPGU Tech. This book I'll open. You all have the soft copy of this book?
Yes,
Yes,
sir.
sir.
Okay. So you just see this point of time. After that, you can refer this book. So we are at this MV history. So this we are going to study now. What is MV history? So there are some scenarios where we need to search for some value or the key in the minimum time maybe. Okay, so number of comparison should be less. For this, such type of MV search tree has been developed. Okay, so uh, here we'll also go through this B tree, B plus tree, which is a part of MV search tree. So you can see here MV search tree are generalized version of binary search trees. Okay, so the goal of MV search tree is to minimize the access while retrieving a key from a file. Okay, so ये होता कैसे, we'll see about it. Don't go for all this thing. So just come to this definition part. An MV search tree may be an empty tree. It may be empty, but if when T is not empty, then there are some properties that need to be applied. The first thing is what? For some integer m known as order of the tree. This is very much important. What is the order of the tree? That is each node is of degree which can reach a maximum of m childrens, you can say. Okay, so m child node should be there. Suppose the order, suppose the order example. So the order of the tree, suppose it is 3, then it can have 3 children. 3 children like this. 1, 2, and 3. Okay, and these are child 1, child 2, child 3. It can have 3 children. But the key 1, you can say, it can have 2 children. Okay, and we have key 2. So this is one child and this is one thing. So if there are 3 children, then there will be 2 keys. Okay, suppose order of the tree is what? Order of tree is what? 5. Then how many key will be there? There will be
4.
4 key. Yes. 1, 2, 3, and 4. So one child will be here, child 1. One will be here, child 2, child 3, child 4, and child 5. And there will be 4 keys, K1, K2, K3, and K4. So this is what. Suppose there are or the order of the tree is 6. Then how many keys will be there?
5.
5.
Five key and six child. Okay, if child count is seven, then how many
6.
key will be there? Six. So you can
6.
say if there m, the order of the what is the order of any node or order of the tree is suppose n, then or m you can say the order of the tree is m. Then how many key will be there maximum?
M minus.
M minus 1.
M minus one. Yeah. So maximum key and you can see the number of children. So this is all about this. Let me admit. Okay. So we'll see what this representation is. So the keys, the count of the key will be at 1 to m minus 1. That is a ki. The number of keys are what? 1 to m minus 1. Okay. So we'll see about it now. This is one example. You can check. That is example 7.45 in the book. You can check here like this is what the order of the tree is what 5. Okay, so it can have 5 children and the keys are 4. So you can check this. So an example of 5-way search tree is shown in figure 7.45. Observe how each node has at most 5 child nodes and therefore has at most 4 key contained in it. The rest of the properties of a search tree can also be verified with the example. Okay, so in this, I'll just open a marker here. So you see here, at this node, at the root node, you can see how many keys are there?
4.
4. And how many children are there? 5. Okay, so this is completely filled. This is full. Okay, it the property of 5-way search tree is satisfied here. But once we include any other node here, suppose we want to include some node like 400, for example, so it cannot be put here. We cannot put 400 here because it is already full, so we need to break it. If some new node need to be added here, then we need to break it. So we'll see that break property when we'll study about this b tree, b plus tree. Till then you just see this concept. So here there are 4 keys and we have 5 child. Now you see the key in the left child of this 18. So this the left child of this 18 or the left subtree of this 18, what? This is the left subtree. Yes or no? Okay. Can you see the left subtree?
Yes, sir.
So all the value in the left hand side are what? Are less than 18. You can check here, that is 7, 12, 8 and 10. All the value here in the left hand side are less than 18. Okay. So whether it be 7, whether it be 12 or 8 or 10. Okay. You see about this 10 and 8 and 10. So it is between 7 and 12. So all the value at the right hand side of this 7 is greater than 7 and is less than 12. So some property of binary search tree is being followed here. Okay. So it's a specialized kind of binary tree as we have seen here. Okay. Tree, this is a generalized version of what? Binary search tree. Okay. So यहाँ तक समझ में आ गया आपको क्या हो रहा है? Coming to this part, this subtree. The right subtree of 18 is null. There is no right subtree. There is no right subtree of this 44. Okay. but we have a right subtree of what? 76. So all the value, all the nodes or the keys in the right hand side of this 76 are greater than 76, whether it be 77, 18, 92, 141 या कुछ भी है वैल्यू, एंड 198 से वो वैल्यू क्या होंगे? छोटे होंगे. ओके, क्लियर है ये चीज?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Think of the scenario where you have to develop such tree using a binary tree. Then what will the length of that tree? The length of that tree could increase. Okay? Because we can only accommodate one value in one node. Okay? Or two nodes in one generation. Yes or no? Two or in power of two.
Yes, sir.
So the level will increase, but the advantage with MVSS tree is what? We are reducing the levels. It is a kind of a fat tree. Okay, it's not a what is a long tree. It is a fat tree. So the first operation that we need to perform this MVSS tree is what? Searching. So how searching is being done? Suppose in this example it is shown that suppose you want to search 77 here. So what you need to do? Please let me know, anyone. What you will do first? Let me know.
Sir, first we will compare in root node 18,
Yeah,
44 and
first we will
76.
start with the root node. Okay, then what we'll do? Okay, so I'll tell you. First, we'll check for the 77. Suppose you want to so 77, so we'll go here. We'll check, is it present here? No, but it is greater than 76. So we'll go to the right child of this. So we'll again compare for this 77 here. Then we'll again check, it is less than 77 should might be less than in the 80, and it should be there in the left child of this 80. So we'll go here, we'll check for this 77, and we have found 77 here. But in the somehow we want to search for suppose 15, or we can say 9. Suppose we want to search 9. So we'll just check at the root the value 9. We'll see that it is less than 18. We'll go to the left hand child. We'll again check for this 9 here. It is greater than 7 but less than 12. So we need to check this tree. So we'll again go here. We'll check for this 9. It is greater than 8, less than 10, and all the leaf nodes are null here. So we can conclude that if we are searching for 9, then it is not present here. It is not present here. Okay, so the search is unsuccessful. With 3 to 4 comparison, we came to know that 9 is not there. Okay, but if we compare this with the binary search tree, then we need to go to the deep level. Okay, to a level which might be of what we say length n. But here the size or the length of the tree is reduced. समझ में आया सबको कि ट्री का जो लेंथ होता है वो रिड्यूस हो जाता है इसमें. Okay, the depth is very less. So here if you see to search 13, we begin at the root. As 13 is less than 18, we move down to the first subtree. Again search 13 greater than 12. We proceeded to move down the third subtree of node, but fall off the tree having encountered a null pointer. Because tree has a null pointer, then we can conclude that this 13 was unsuccessful. The search for 13 was unsuccessful. In place of 13, I have considered 9 in the example. क्लियर है आप सबको कैसे काम करेगा एमएस सर्च ट्री? कोई डाउट है तो आप पूछ सकते हैं. And if you have any doubt, you can ask me.
So if we got an element between, let's suppose, 18 and 44,
Yes.
so it will be greater than 18, less than 44. For that, we need to that just move that null pointer to array. We have to just give it to that, and that will
If it
make
is not
another.
null, if it is null, then we'll stop the search here by concluding that yes, the element is not present. But if there is some tree here, some child node is there, then it is our duty to check for that element in child node also.
Okay, so sir, in this basically we are increasing the width of the tree more and more,
Yes, we are increasing
reducing
the
the
width.
level of the tree.
Yeah, reducing the level because this will, what we say, provide you the efficiency while searching of any element.
So one
Number
more
of
thing,
comparison will be reduced.
sir, if there is a, I want to insert an element like between 7 and 12, I want to insert 8, so I can do that.
Yeah, you can do that. Yes.
But we cannot exceed that, like the maximum element it will take will be 4. We cannot exceed from that thing.
Yeah, you cannot exit from that. Okay,
Got it.
suppose you want to insert, suppose, what is it, 15. So you can insert 15 here. Don't need to worry. Okay, even you can insert one more element, but you cannot insert other than that. Okay, you cannot exit that element. The order of the tree must be maintained. If it is a five-way tree, five-way search tree, then it should have five child, not the six child. Understood?
Yes, sir.
So that is the thing here. Suppose
So for
you
this, we have to use sorted data only, no?
no, it is not like sorted data. If you insert an element, we'll show you how to insert an element in the next example. I'm referring book only because it will help you in understanding the concept from the book. That will motivate you to read a book. So I'll just tell you the next example that how to insert an element in any MV search tree. So let's go directly to that. See. So what is the order of this tree? Three. Yes or no? Three-way search tree. सबको दिख रहा है ये? Three-way search tree. So it means what? It may have three child. And how many key can be there?
2.
Two.
Okay. Two key can be there. Three child and two keys. Maximum. So number of child is what? Three. Number of keys, tell me. Number of keys, two.
2.
Suppose you want to insert this DKP, DKP VAG. So first D is inserted. Okay, there is no child here because this is a root node. D is the single node. Then it is not exceeding this degree also. Okay, then K. Then what is a where we insert two node here like D, two keys here, sorry, D and K. D is one key, K is one key. Then we can have, at most we can add three children. Can you see here? If you add two nodes, we can add three children here. Yes?
Yes, sir.
Yes, sir.
Okay. So once we insert this D, so we can have the left child, right child, which is null at this point of time. But we insert this D and K. So we can have the left child of this, we can have the right child of this, and we can have again the right child of this. So you can assume this diagram like this. D, K. Okay. So this is what? This is having 2 keys and 3 children. Yes or no? Okay, so order of the tree is what? Is 3 and it is exceeding that. Suppose if we insert any other node here, any key here, then it will exceed this property. So we'll do so. Let us see. Now we need to insert was P. P we need to insert. Then where will insert P? P will insert in the right hand side of this because P is greater than K. So it will like this. This is null, and it is greater than this. So it is having P and it is having left child as null, right child as null. Okay, is it clear to you all? क्लियर हुआ देखो एक बार और बना देता हूं मैं it is P, it has a left child, right child, both are null. ठीक. Now if you insert V here, V is also what? Greater than K. Then it will be like this. Okay, clear? So it is like this.
Yes,
You
sir.
can check here. Yes, sir. Okay. Now again we will insert this A and G. So this is what? A and G. Okay. So earlier the left child of this D was null, right child of D was null. But here if you want to insert A and G, so we'll insert like this. Suppose if you want to insert A, it is less than D, then we'll insert here. A हम यहाँ पर insert कर देंगे. Okay. And suppose now if you want to insert G, then we can insert it here because G is greater than D and less than K. So we can insert here this. Okay. Clear?
Yes, sir.
Okay.
Yes, sir.
Now, when we'll study about this B tree, B plus tree, we'll also check for this balance factor now. Okay, we'll balance it, how we can break it, we'll check all these things. So till then, you just remember the concept of this B tree. Now coming to this deletion part. So all of you are comfortable with this insertion part now?
Yes, sir.
Yes, sir.
हाँ sir. Okay, so let us discuss about this now. Deletion part. So I'll just give you few example about it. Let me first include it. Like 18, we have then 44, then we have 76, then we have 198 as per the book. Okay. Now the left hand child of this, like it is what? It is what, like 6, then 7, then 12. Okay. This one. Then again, as a right child of this, I'm including here like 19, then we have 30, like this. Suppose I want to delete 18. Okay. सबको दिख रहा है ये एग्जाम्पल? एवरीवन?
Yes, sir.
Yes, sir.
ठीक है, अगर मैं ये 18 को डिलीट करना चाहता हूँ, ओके, इफ आई टू डिलीट दिस 18, देन व्हाट आई नीड टू डू? आई नीड टू keep any child in place of this. If you delete it, I cannot put it blank. I need to put some element here. So what will be that element? The element can be the greatest from this left hand side. Greatest from left subtree or the left child. And it should be greater the smallest from the right child or right subtree. अंडरस्टूड? क्या करेंगे हम लोग यहाँ पर? So we
Yes, sir.
can, if we delete 18 here, we can keep here 12. So when we keep 12, we can still, what we say, without disturbing any other element, we can still maintain the property of this tree. So all the element in the left hand side will be what? Less than 12, and all the element in the right hand side will be greater than 12. Yes or no?
Yes, sir.
Now, suppose if we keep here, instead of 12, if we keep here 19, then again this property follows. All the element in the left subtree will be less than 19, and all the element in the right side or at the right child is greater than 19. So the greatest from this left child and the smallest from the right child is replaced in place of this parent. Okay. क्लियर है आप सबको ये?
Yes, sir.
Yes, sir.
So यहाँ पर example है. It is also telling you about the deletion concept. Deletion in a M-based search tree. So in a M-based search tree, you see here, this is the earlier tree. You see here 262, 272, 286, 350, and 6, 7, 12, 8, 10, 77. So you just refer this first. Okay, how deletion is performed. 262, 272, 286, and 350. So when 262 is deleted, so the smallest from the right child is taken over. So the value 272 is kept here. Okay. So when we have deleted 262. But and again if you delete the 12, you can see if you delete the 12, then this from 8 and 10, you can see here from 8 and 10. The greatest from the left child is taken here. Okay, so 10 has come here. So this is how we still maintain the property. Is it clear to you all?
Yes, sir.
So there are some properties you check here. How deletion is being performed. So if AI and AJ is null, if there is no left child, if there is no right child, then we can directly delete it. If the left subtree is null, left there is no left child, but we have a right child. Okay. Sorry, I am telling you the other thing. If left hand child is not null, if it has a left subtree, and if right child or there is no right child or the right subtree is null, so means we need to check the largest of the element from the left subtree. So to then choose the largest of the key element k double dash in the child node pointed to by aj. Okay. Now, if the left there is no left subtree or there is no left child, then and we have a right child, okay, that is not equal to null, then we need to select the smallest of the key element from the subtree. Okay, so the smallest element in the subtree, or you can say the in order successor or predecessor we can take, okay, and make it as a or replace that element as a key in the root. Okay, that we can do. Okay, if both are not null, then we can, it is our choice that which value we can replace, either greatest from the left subtree or the smallest from the right subtree. It is totally depending on our decision. Okay, clear to you all?
Sir, there is no any preference.
There's no preference. Preference is the only thing. The priority is that the greatest from the left and the smallest from the right subtree. In other words, in binary tree, it is in order successor or predecessor. Okay, that is the only preference. Clear?
Yes, sir.
Okay. So now we'll study about this B tree and B plus tree now. So it is a kind of B tree. Okay, so M-based search tree have the advantage of minimizing the file accesses due to their restricted height. However, it is essential that the height of the tree be kept as low as possible, and therefore there arises a need to maintain a balanced M-based search tree. So the M-based tree we are studying is not balanced. That's why we are not rotating or what we say breaking any node, but here there is a need of breaking a node. If at any point, if the number of node exceeds what we say exceeds the limit, okay, exceeds the order of the tree, then we need to break it in order to make it a balance. बैलेंस होता है तो क्या होता है, और लेवल्स का वो गारंटी हो जाता है कि इतने कंपैरिजन ही लगेंगे बस. ओके, उससे ज्यादा एक्सीड नहीं कर पाएगा. दैट इज द एडवांटेज ऑफ दिस बी ट्री. ओके, सो इट इज अ काइंड ऑफ एम ट्री बट इट इज अ बैलेंस थिंग. तो अब यहाँ एवीएल ट्री आप जो कर रहे थे बैलेंस करने के लिए, एक एवीएल आप समझे थे और एक एमवे है. नाउ वी नीड टू मिक्स दिस बोथ. दोनों कॉन्सेप्ट आपको यूज करना है. ओके, सो बी ट्री इज वेरी वेरी इंपॉर्टेंट. So यहाँ क्या है definition we can check. A B tree of order m if non-empty is m-way search tree. So the root has at least 2 child node and at most m child nodes. So this is one property, that it should not, the root should not be less than what we say one key. At least one key should be there. Okay, it should contain at least 2 child and at most m child. क्लियर है ये चीज?
Yes, sir.
ओके, एक और इसमें प्रॉपर्टी आता है. सपोज जो इंटरनल नोड्स होते हैं, रूट को छोड़ के जो इंटरनल नोड्स होते हैं, ओके, विच आर नॉट द लीफ नोड बट दे आर द इंटरनल नोड्स एक्सेप्ट द रूट नोड, उसमें एटलीस्ट m/2 चिल्ड्रन होने चाहिए. सपोज ऑर्डर ऑफ द ट्री इज गिवन लाइक 6. 6 इज द ऑर्डर ऑफ द ट्री, m की वैल्यू 6 है, तो इंटरनल नोड में एटलीस्ट हमारे पास कितने होना चाहिए? 6, सॉरी 3 चाइल्ड होने चाहिए हमारे पास. ओके, ये इसकी एक प्रॉपर्टी है. एंड एट मोस्ट इट कैन हैव 6 चाइल्ड. एट मोस्ट 6 चाइल्ड एंड मिनिमम 3 होने चाहिए. एक और 2 चिल्ड्रन नहीं होंगे इसके. तो दिस इज वन प्रॉपर्टी दैट हेल्प्स इन मेकिंग इट अ बैलेंस काइंड ऑफ थिंग. ओके, तो ये कैसे होगा, क्या होगा, विल स्टडी इन द नेक्स्ट क्लास. Since it's an online lecture, it's very difficult for you to just focus too long. I can teach this, but I am sure that you will be also requiring a break. So we'll study about this B tree, B plus tree in the next class tomorrow. Okay, is it okay?
Yes.
Yes, sir.
Yes, sir.
Okay then. Now tell me the attendance.